Now we are starting the second part of spectrophotometry lectures, which is absorption of radiation or absorption of light. Still the same chapter, fundamentals of the simplest device for absorption will require light source or simply a lamp. Now light is coming through this sample. It's helpful to have monochromator or filter or wavelength selectors, so we'll not be measuring all light but some selected photons which are collected by detector, and then we have data processing. Alternatively, we can put monochromator ahead of sample, so sample will not be exposed to that many photons and maybe will not be bleached by photons. Both approaches are essentially very common. Now this figure depicts attenuation of beam of monochromatic radiation, so beam is coming here, as it passes through absorbing solution with thickness of B and concentration C of moles per liter. Because photons interact with particles in solution, radiant power decreases from P0 to P. It always goes smaller. You can absorb photons. You cannot create photons out of nowhere. Transmittance of solution is fraction of incident light, P, transmitted by solution. So T is P divided by P0. Sometimes, mostly because of tradition, is expressed as percentage and called percent transmittance. So P0 multiplied by 100%. It's confusing unit. Try to avoid it as much as you can. Absorbance A of solution is related to transmitted in logarithmic manner. Notice that when absorbance increases, transmittance decreases. Less light coming out, larger is absorbance. More light is absorbed, less is coming out. Scales at early instruments were linear on transmittance. Modern instruments, computer calculates absorbance from measured quantities. So A minus log T is log P0 to P. Absorbance can be calculated for percent transmitters as well. So minus log T, 2 minus log T percent. Transmittance and absorbance, as defined, usually cannot be measured because solution must be held in a cuvette or cuvette cell. Reflections and scattering can occur at walls, as it's shown on figure. These losses can be substantial. For example, more than 8% of beam of yellow light lost by reflection when it passes through glass cell. Light can be scattered from surface of large molecules or particles of dust in solvent, and this scattering causes further attenuation. To compensate for these effects, power of beam transmitted through a cell-containing solution is compared with that traverses exactly the same cell containing only solvent or reagent blank. Because of this approximation, terms P0 and P will be used to power of beam that has passed through cell-containing solvent and in a light solution. So we are not taking into account this Walls effect and side effects of scattering. We'll try to discuss them on later date if we'll have to. Now, Bear's law, not beer. It's not beer. A bear was a German name, so we pronounce bear it in German. I don't care how you'll pronounce it actually. According to Bear's law, absorbance is proportional to concentration of absorbing species and to the path length b of absorbing media. A is minus log t, A, B, thickness cuvette, and concentration. A is proportionality constant, called absorptivity. Now, absorbance is unitless quantity. Absorptivity must have units that remove units of thickness and concentration. If concentration is in grams per liter and units in centimeters as usual, absorptivity will have units of liters per gram and centimeter. Now, most commonly we express concentration in moles per liter, which of course is molarity, and thickness of cuvette in centimeters. Then proportionality constant we call molar absorptivity and given symbol of Greek letter epsilon. So minus log T is epsilon Cl and its absorbance. What's important? This is straight line. Absorbance is straight line as a function of concentration. The units we are using are not the only in use. So for power units, we say radiant power, transmitted radiant power. Absorbance is log P0 by P by definition. Transmittance is P by P0. Path length of sample B. Now we have absorptivity and more important molar absorptivity. There were old units and you often will find them, especially in medical books. Optical density instead of absorbance, extinction instead of absorbance, transmission instead of transmittance, and molar absorption coefficient instead of molar absorptivity. Try to avoid these old units as much as you can, but you should be able to read them, especially in clinical analysis. Now an example. 725 10 to the negative 5 solution of potassium permanganate has transmittance of 0.441 when measured into 2.10 cell of wavelength 525. Calculate absorbance of this solution and molar absorptivity. Now if we have transmittance, we simply take in log of this and we have absorbance value, change in sign. To have molar absorptivity, we take absorbance and divide by thickness of cell and by concentration, and we have the value. Bear's law applies to solutions containing several absorbing species. If these species do not interact, total absorbance will be simply the sum. So if we have component 1, component 2, 3, 4, all the way to n, you'll have Bear's law for 1, Bear's law for the second, and Bear's law for all others. Subscript ratios to components 1, 2, so on. Absorption spectrum is a plot of absorbance versus wavelengths as illustrated here. So wavelengths, absorbance. Sometimes absorbance is plotted against wave number or frequency. Modern scanning spectrophotometers produce such spectrum directly. Now, when it's singular, we say spectral. When it's plural, 2 or more plots, we say spectra, similar to Latin. So here you see spectra for several concentrations shown here in ppm. A cell length is 1 centimeter. plot will be linear and absorbance obeys Beer's law. Spectra can be different if you put the same compound, in this case it's tetrazine, in different media. In vapor, you can see plenty of peaks which are very sharp. All the vibrations and rotations are available in vapor. In hexane solution, movement of molecule is more restricted, so you have much wider peaks, still resembling vapor to some extent. When you are coming to water, you have very wide peak with only one maximum because of plenty of intermolecular interactions in water, for example hydrogen bonding.